Good evening. Welcome to the second lecture of this lecture series, Physics with Partha. In this lecture, we are going to talk about kinetic theory of gases. So before going into that, let's quickly revise our previous class where we have learned about notion of heat, zeroth law of thermodynamics, then concept of temperature. We have learned scales of temperature, which are basically three scales: Kelvin scale, centigrade scale, and one random scale we have assigned, and we have seen the interconversion of temperature from one scale to the another. Then we have learned triple point of water, which is basically water coexisting in three phases: solid, liquid, and vapor. Then flow of heat, conduction, convection, and radiation, three mechanisms we have just introduced. Next, thermal expansion, three kind of expansion we have learned: volumetric, superficial, and linear expansion. Then we have seen anomalous expansion of water. In this video, we are going to cover introduction about kinetic theory of gases, assumptions of kinetic theory of gases, then calculation of pressure of an ideal gas. As you can see in the adjacent picture, that the hard sphere, which are red dots, those represents gas molecule, which is given within a cubic box. We have seen that gas molecules are randomly moving in a cubic box. Now we are going to learn how they move, what kind of phenomena are going to happen due to this kind of movement, and then interrelation among these different state variable, which we have learned in our previous lecture. We have just introduced the concept of state variable, which are basically pressure, volume, temperature. Okay. So if we observe the figure in the left hand side, we can see one cubic box where we see that the molecules of ideal gas is written, which are represented by different small spheres. Next, we can observe that elastic collisions with the walls is written. That is meant to say that those gas molecules are undergoing elastic collisions with the walls. Next thing is, lots of empty spaces are there in the picture. That means whenever we are considering a particular volume of a ideal gas or any kind of gas molecule, then there are a lot of empty spaces available. Next, all molecules are in random motion, which you can observe. Here, the ideal gas equation, we can see that PV equal to nRT, which the symbols represent usual meaning. Those are marked by arrows. In the next picture, we can see the compressibility of a gas is written. That means one property of gas molecule is that we can compress the gas molecule within the container where it is contained. If we apply some external pressure, then the gas molecules undergo compression. So this property is illustrated in this figure. Okay. Let's talk about the assumptions of kinetic theory of gases. All gases are made up of molecules, which are in constant random motion in all directions. The molecules in a gas are small and very far apart. That means the size of the molecules are very small and they are far apart. So if we compare the dimension of gas molecules with the distance separating two molecules, then the dimension of the gas molecule is very less compared to the distance of separation between two molecules. The molecules exert no force on each other and the wall of the container except during collision. So the momentum transfer occurs only during collisions. That is meant to say that the molecules are made up of atoms. An atom within itself has a nucleus, and that nucleus is exerting electrostatic force of attraction to the electrons of the gas atom. But in ideal situation, no two molecules exert any such kind of attractive or repulsive force in an ideal situation. Now, whenever they collide, they impart momentum. They change momentum, they transfer momentum from them to the wall or among themselves. Next, when collisions occur, when collision occur, the molecules lose no kinetic energy. That is, the collisions are said to be perfectly elastic. So basically, there are different kind of collisions that may be inelastic, that may be elastic. That depends upon coefficient of restitution, which we have I think we'll learn in our some of the later lectures. So now the total kinetic energy of all molecules remains constant as well as the momentum is conserved. So thus, just for your information, for any kind of collision, the momentum is conserved. But in case of elastic collision, kinetic energy is also conserved with momentum. Next is the time spent during the collision is very less. Okay, the molecules obeys Newton's laws of motion. That means we can represent the gas molecule as classical particles. When a gas is left undisturbed for sufficient time, that means no external pressure, no external force is applied to the system. Previously, we have shown you a figure of compression, or that can happen the other way around. It can be expansion also. Now, in this case, we have set some primary condition and kept the system undisturbed. That means to say that the system will reach equilibrium or steady state after some time. Now the density and the distribution of molecules with different velocities, that means the kinetic energy, are independent of position, direction and time. That means under steady state, if we observe a particular volume within the cube of gas molecules, then the density, velocity, those aspects are independent of position, direction and time. This assumption is justified when there are lots of numbers of gas molecule, that is numerous gas molecules is present at that instant. This assumption is valid. Now we are in a position to calculate the pressure of an ideal gas. So let's check how it is calculated. Here in the left hand side, the picture shows a cube where we have marked the area A1 and A2 that is facing each other. The x, y and z axes are specified. The length of each side of cube is capital L. Now at a particular point A, we assume a gas molecule as shown by a dot. It is written that the direction of velocities are Vx, Vy and Vz. So here molecules, that is gas molecule, are assumed as hard sphere, and that means the molecules are sphere like shape, and we have assumed only one molecule for this derivation that can move randomly in any of the direction x, y and z. That is why the velocity of the molecule v is represented as Vx vector addition of Vx, Vy and Vz. Now, as we have written that, assume a volume of a cubic shape with side length L. Consider a molecule inside the cube having velocity v, which is the summation of the components. Next, consider only x direction where Vy and Vz are kept constant. Now in only x direction, we are telling that the molecule is moving. So molecule at position capital A starts moving in plus x direction with velocity Vx, then it collides with the wall capital A2, and then it rebounds with velocity minus Vx. So here we neglect the collision among the gas molecules since we have assumed only one molecule inside that box. Next is assume that only collision with the walls of the container, and that is too elastic in nature. That means the kinetic energy and momentum are conserved, and here no deformation is associated with this collision event. Now let's look at the momentum. So momentum of the gas molecule when it is traveling towards capital A2 area is P1 equal to mvx. When it is rebound, then the momentum is minus of mvx, where small m is the mass of only one molecule. Now the change in momentum will be P2 minus of P1, which is minus of twice mvx. The black arrow head is headed towards the change in momentum of the particle. Now, since this collision is elastic, net momentum of the system must be conserved. That is, the system is walls and the gas molecule all together is the constituent of system. So, the change in momentum of the wall should be plus 12 of mvx. As a result, the net momentum change is 0. Now, this we can look at as elastic collision. The black box shows that if we consider P as the momentum which is conserved within the system, where for any general particle capital A and the wall A2, we can tell that mass of the particle is small m and the mass of the wall is very large compared to that small m mass of the particle, so which we tell as infinity. Now initially the wall is at rest, so or infinity is a very large number, so we assume that capital M is the mass of the wall. So initially, before collision, the initial momentum of the system, that is the particle and the wall, is small m bx initial plus capital M into 0. That is, wall is not moving before and after the collision. So that is given by P1 momentum. Now after collision, mass of the particle small m vx, velocity of the particle final velocity vx final plus capital M into 0. Even after collision, the wall is not moving, only gas molecule is moving. That is why we assume m into 0, which will give us the final momentum P2. Now as per the law of conservation of momentum, P1 equal to P2, which gives us m into vx initial equal to m into vx final. So magnitude of, from here we can tell that magnitude of initial and final velocities are same. So we need to assign the sense of direction by ourselves looking at the system, which we have assigned. If we go little bit go back towards the left side, here the enlarged version of that figure is again shown by capital area A1 and capital area A2, where Vx is the velocity of the particle along positive x direction and minus Vx is the velocity along negative x direction. Now here we can see that the particle collides with the wall A2 with capital velocity Vx positive, and then after that it rebounds with the same velocity, that is same magnitude of velocity, but the direction is altered. Now let us calculate the time taken to reach from A2 to A1 is capital as L is the length divided by Vx is the velocity, which is given by T1. Capital A1 to A2 is L by V2. So the molecule is colliding back and forth with the walls of the container and moving in between. As a result, the time taken between two consecutive collision will be, that is molecule colliding with A2, then going towards A1 and again coming back to collide with A2 is T1 plus T2, which is given as twice L by Vx. Okay. Hence, the time taken by the molecule between two consecutive collision with capital A2, that is that particular wall, is delta T equal to 2 capital L by small Vx. Now, number of collision per unit time would be 1 divided by this particular time delta T, which is given by small n, that is Vx by 2L. So we know that force into time gives us the impulse, that we call force into time is called as impulse. We learn it from our Newton's law, that is the basic physics in class 11 course, that is given as change in momentum delta P, which is equation number 1. Now momentum transferred to the wall in one collision will be delta P dash equal to 2 mvx, which we have already seen in our previous slide. So momentum transferred to the wall is this, twice mvx. Now per unit time if we consider, then we need to multiply the momentum transferred to the wall into frequency of collision, that is how many number of collisions are happening in a particular amount of time per unit time, that is n into delta P dash, which is Vx by 2 capital L into 2 mvx, which will give us small m by capital L into Vx square. So hence here the time is unity, that is force, we have written it as force, that is already in equation 1 we have seen that force into time equal to transfer of momentum, that is change in momentum. Here we have taken time as unity, that means force will be equal to that transfer of momentum, that is small m by capital L into Vx square. Hence the total force on capital A2 due to all the molecules. Now we bring into the other molecule to the system. Previously we were looking at the interaction of the wall with only one molecule, but in reality in that particular volume lot of molecule will be there. So now we bring in the other molecule and we tell that the overall force is capital F equal to summation over the number. Here H symbol gives you the number, summation over the number over the force exerted by one particular molecule, that is m by L into Vx square, which is m by L summation over Vx square. So the molecules are not only moving in only x direction, they are moving in other directions also. That is why for every direction like x, y and z, we can tell that the average of these velocities in x, y and z direction are 1/3 of Vx square, Vy square and Vz square, since the velocities are equiprobable in all the direction. That is given by 1/3 of summation over Vx square, V square. Now from equation 2 we can tell that capital F equal to m over 3L summation over V square. Say capital N number of molecule are there. Now we are quantifying how many number of molecule are there. That is capital N. Mass of each molecule is small m. So as we know that force equal to will be 1 by 3L. 1 by 3L, we are writing the previous equation only. 1 by 3L small m into capital N we are bringing in, divided by capital N. Capital N is multiplied in the previous equation, nothing else is done. So summation over V square divided by N. It is written as a separate term. So where capital M is the mass of all the molecule present, since mass of single molecule is small m into number of molecule will give us the mass of all the molecule present in the system, that is small m into capital N. L cube is the volume of the cube. So density is mass by volume, small m capital N divided by L cube. And then pressure, as we know, it is the force exerted per unit area. The system we are considering is the wall, which is having area L square. So pressure is force by L square, which is given as 1/3 of mn over L cube summation over V square over N. Finally, we have derived an expression of pressure as P equal to 1/3 of rho, that is the density, summation over V square upon N. So here we need to remember that pressure is having this expression. Now summation over V square, we can term it as RMS velocity with V square RMS. Now density, as we have written, mass by volume. Then from here we can write that PV equal to 1/3 of capital M V square. So this is also another form of ideal gas equation, PV equal to 1/3 of M V square, where again we can write it as PV equal to 1/3 of Mn V square average. So which is same as V square RMS. Now summation over V square we can tell as V1 square plus V2 square Vn square. If capital N number of molecule are there, then their velocities are squared and then summed. Then if we take under root over there, then we can tell that root means square velocity. So this is not velocity, this is speed, average speed. Okay. Let's quickly summarize what we have learned today. At first we have learned the ideal gas equation, which is given by PV equal to nRT. And for your information, this equation is valid for any kind of gas at low densities. Okay. So calculation of pressure we have learned. How to calculate the pressure of an ideal gas. We have derived the detailed expression of that. You can go back and look at it carefully. And if you have any doubt, so let me know. We have written that P equal to 1/3 of rho V square, where V is the RMS speed, V square is the RMS speed. Okay, density, where rho is the density, V is the mean square speed, that is RMS speed. Capital M is the mass of the gas, total mass of the gas. So we can express it in another way, PV equal to 1/3 of capital M V square average. And then again another form of it is 1/3 of capital N small m V bar square. So total number of molecules is capital N. That is the total mass of gas equal to mass of one molecule into number of molecule. That is capital N into small m is replaced by capital M. Okay. Next, RMS speed we learned that the root means square. As the name suggests, it is the speed given by under root of summation over V square divided by capital N. Okay. So V average square equal to V RMS square, as we have seen here, V square equal to V RMS square. So hence pressure is again termed as 1/3 of rho V square RMS. From there we can find an expression, closed form expression for V RMS, which is under root 3P over rho or 3PV over capital M. So these relations we need to remember for our next portion to come. Okay. So thank you for your kind consideration. So in our next lecture, we will learn about the other aspects of kinetic theory of gases, which will demonstrate some of the kinetic interpretation of temperature, some of the topics like this, then deduction from kinetic theory, a little bit about Maxwell's speed distribution law, then thermodynamic state, Brownian motion, vapor, evaporation, other things are there. So please stay connected, and if you have any query, please let me know. And if you need any kind of clarification justification, then also you can write me at physicswithpartha@gmail.com. Okay, thank you. Thanks a lot.